Yeah, I opened the YouTube link now.
Yes, sir, you are live.
Should I start?
Yes, sir.
Should I start?
Yes, sir, please.
Okay. So hello student. So today we have our live session, last live session. And in this live session, I like to discuss about the last topic, which is interesting, and that is the nonlinear waveguides, mainly nonlinear fiber-based waveguides. So if you remember, in the lectures, we initially started the basics of nonlinear optics, from where the nonlinear optics basically appears. And it is essentially the electric field and the interaction between the medium, and the response is nonlinear. If the response is nonlinear, then you will going to get a nonlinear stuff in the system in the form of higher harmonic generation and other few phenomena are there. Very interesting phenomena are there. Now, we started with the plane wave interaction with the medium. And when you launch a plane wave with a particular form, and if the intensity of this plane wave is high, then essentially what it does, it basically dislocate the electron cloud. So as a result, what happened that some kind of polarization will appear in the system. In linear domain, this polarization is normally proportional to the applied electric field. And if the electric field is high, the intensity of the electric field is high, then the polarization that generate inside the medium is not linear. So it is basically not related to the first order of electric field, rather higher order electric field are associated with that. So this vibration, that means the dipole that will going to vibrate under the applied electric field is no more harmonic in nature. There are some anharmonic components are there, and that makes the system nonlinear. For linear response, we find that the polarization, which is essentially a vector quantity, should have three components, x, y, and z. And these three components should individually proportional to x, y, and z. And this happens for linear response. On the other hand, for nonlinear response, what happened that this px, py, and pz no more proportional to ex, ey, and ez. So as a result, we never have any kind of linear response, and we need to treat the system in a different way. So what happened if I introduce the higher order terms in the expression of the polarization? That expression already discussed in detail in the course. But if you look back to your polarization expression, then you will find that this polarization can be correlated to the three different component x, y, z of the applied electric field. And these components can be written, for example, px, it is x component of the polarization, can be written in terms of the x component of the electric field, y component of the electric field, and z component of the electric field. If you write that, then the entire system can be written in a well-defined matrix form, And then we define something called susceptibility, which is essentially a matrix quantity, which is essentially tensor rather. So different kind of notation was used. One is the scalar notation, and another is the vector notation, and another is a component wise notation. So you should understand this notation carefully, because if you understand this notation, you will understand that where this summation sign is there and how the components are associated with each other, and how the polarization component is associated with the component of the applied electric field. Now, after considering these three different kind of representation, one is the scalar form, one is the vector form, and another is the component form, we find a scalar form is a very simple way to represent the polarization. And even though this is a simpler version, it can give us a very important information. And this important information is that it tells us how the higher harmonics are generated. Higher harmonics means here the second harmonic or third harmonic. These harmonics are generated, and how it is generated, that one can understand by scalar form. Next, we concentrate about our, so there are many things in nonlinear. So this is the field where nonlinear optics are dominant, but we are not dealing with nonlinear optics right now. So we are dealing with waveguides. So we need to consider this nonlinear phenomena in waveguide structure. And waveguide structure, as soon as I mention about the waveguide structure, there are two kinds of waveguide structure. There are in fact many, but mainly there are two different kinds of waveguide structure that normally we use as a nonlinear medium. One is the silica-based optical fiber, and another is the silicon kind of. Nowadays, it is used very heavily, these silicon waveguides. So both these waveguides are based on certain material that which has a interesting property, and this property is called the centrosymmetric. So molecules of silica and molecules of silicon both are having centrosymmetric structure. Since they are having centrosymmetric structure, we mentioned that the second order susceptibility for this kind of structure is 0. Any even order susceptibility is 0. So only we need to deal with the odd order susceptibility, and then with this odd order susceptibility, we start with the third order susceptibility, and we find that for this kind of waveguides, how the third harmonic generation and these Carr effects become dominating. Typical values one can understand. So the typical values we need to mention here, that the susceptibility, which is a key reason to have a nonlinearity. For second order susceptibility, it should have, it is of the order of 10 to the power minus 12 meter per volt, and susceptibility, third order susceptibility is of the order of 10 to the power minus 24 meters per volt square. So you can see that the value is very, very small. So in order to excite the effect, higher order effect, either you need to increase the amplitude of launched wave or launched field, or you can change the geometry of the waveguide. Geometry is something which is important in nonlinear optics, because you can reduce the geometry in such a way that the effective area becomes very small, and that means the light can be confined to the waveguide to a very tiny region, and as a result, what happened, you will get the effective nonlinearity very high. So nonlinear coefficient gamma, which is inversely proportional to the effective area, will be very high if the effective area is small. Well, after that, we derive the expression for Maxwell's expression, and this from the Maxwell's expression introducing the effect of intensity in refractive index, which is essentially the Carr effect. We can find out that the wave equation is slightly modified, and we introduce the nonlinear polarization as a source term. So these calculations are done very in detail in the course, and from this calculation only you can find out that how the second order effects are generated. For example, if there is a chi2, then you can have a second harmonic generation, because now, because of the presence of chi2, what happened, the electric field that is going to vibrate is proportional to, there will be two parts, one is omega and another is 2 omega. So these 2 omega basically gives you the second harmony. On the other hand, for silica and silicon, when we have a centrosymmetric system in our hand, we have third order effects, and in third order effect, third harmonic generation is one of the major phenomena that one can observe. But you need to remember that this higher harmonic generation is very sensitive to something called the phase matching. So if you want to generate the higher harmonic, the phase matching should be very, very precise. And once the phase matching are there, then you can then only you can able to find out your higher harmonics. On the other hand, there is something called Carr effect, which is the intensity dependent refractive index. That means the refractive index will be now modified under the presence of the light itself. This is a very interesting phenomenon, and this phenomena will appear when chi3, that means third order effect, is non-vanishing. So that calculation is also done, and we find out that there are two, the chi3 has two contributions. One is the contribution for third harmonic generation, and another contribution is for the optical Carr effect. So optical Carr effect is associated with the intensity dependence of the refractive index, and detailed calculation suggests that how the refractive index is modified. And we find a very interesting expression, a very well-known expression rather, which is n is equal to n2i, where n2 is called the Carr coefficient. So that means the refractive index, which so far we know that it is a function of frequency, now became a function of intensity as well. And with these advantage, we can do many things. The Carr effect basically allow us to generate something called optical soliton. In the later part of the lecture, or rather last part of the lecture, we find that optical soliton can be generated. But what is the basic implication of this Carr effect is that it basically generates something called self-phase modulation. So when we launch the optical pulse, then the phase of the pulse will be modified, because when the pulse is propagating inside the fiber, when the electric field is propagating inside the optical fiber or any nonlinear waveguide, it will experience a refractive index change. And not only that, this refractive index change will depend on the distribution of the intensity. So if the distribution of the intensity is such a way that the refractive index is changed in the core region in a maximum way and gradually reduces in the cladding region, or in other way, if you launch a optical pulse having a bell-shaped structure, bell-shaped envelope or a Gaussian kind of envelope, then you will get something called the self-focusing. If you launch a light, the light will experience the refractive index high at the core region, and refractive index is gradually reducing in the cladding path, and as a result, you will find uh, uh, that there is a change in refractive index, but this change is also having a structure. And if you launch a light, it will focus in the core region. This phenomenon is called self-focusing, and you can also calculate the change of the phase, the amount of change of the phase you can calculate. And there in the lecture, actually we give some example that for a moderate power level, if the car coefficient is given to you, by the way, for silica, that means for optical fiber, the car coefficient is of the order of 3 into 10 to the power of minus 20 meters square per watt. So the unit of the car coefficient into this meters square per watt. And if you know what is the effective area, you can calculate the amount of phase change. And this amount of phase change takes place because of the change of refractive index. Well, at this point, I expect from your side, if you are live, if you are listening to this discussion, then I ask you to then I request you to ask me the questions or doubts if you have in your mind, anything regarding the nonlinear optics or any part of this course. Nonlinear optics is important in many application point of view nowadays, and many hardcore research is going on to this topic. If you are really interested to do in your higher studies in the field of photonics, nonlinear photonics, communication, whatever, then this nonlinear, the knowledge of the nonlinear optics and the knowledge of the waveguide associated with the nonlinear phenomena should be very, very handy. So if you have the basic understanding that how the nonlinearity is appearing in the waveguides, how one can tackle with these nonlinear effects, and what are the phenomena behind that. So this kind of knowledge should be very, very useful and handy. And in this course, all these calculations, I try to make it very, very simple way so that you can understand readily that how and why the nonlinearity is come into the picture. Normally, we don't like nonlinearity because if in the communication purpose, it seems that if you have the nonlinearity into the system, the efficiency of your system is reduced. So that's why it is expected that you shouldn't have nonlinearity. But in this particular course, in this chapter, we find that nonlinearity is not that bad at all. It can compensate a very important phenomenon, which is called the dispersion, and one can generate the distortionless propagation, which is optical solid, the concept of optical solid. So that thing also we cover here in this course. We find out what should be the form of the pulsate in an optical waveguide in presence of dispersion separately, in presence of nonlinearity separately. And we find that when we have only dispersion, the optical pulse that you launch will broaden in time domain. This is called the temporal broadening. However, when you launch an optical pulse in a medium, nonlinear medium, and it is experiencing only nonlinearity, if I ignore the dispersion part, what it will experience is a spectral broadening. There will be a spectral broadening, and it is a direct consequence of cell phase modulation. So if you calculate the cell phase modulation, you will find that this basically gives a frequency distribution, and this frequency distribution gives you the generation of different frequency components. And as a result, what happened if you launch a light with a particular frequency, in the output you will find that there is a spreading in the frequency components. So in dispersion, we get the spreading of temporal pulse. So that means a pulse that is broadened in time domain. And for nonlinear effects, we find that the pulse is broadened in spatial domain, and I will have a compensation. Maybe I will have a compensation, and we will get something called optical solid. Okay, we got our first question. So by Pritam, and the question is that can you please explain the normalization of nonlinear Schrodinger equation? Okay, so this is not very, I mean, nothing much to explain, but still Pritam asked the question. I like to mention that the equation is normalized for our benefit. If we have to solve this equation numerically, normally we do that. So there is a process called split step Fourier method through which you can solve this equation numerically. Then it is expected that you can make it normalize. What is the meaning of normalize? If you look carefully the formation of the equation in my class notes, then you will find that the equation, the raw version of the equation is having some sort of unit. It was, if you go back to the nonlinear Schrodinger equation, you will find that if psi is a field, so there are a few terms like del psi, del z, the first order derivative with respect to the propagation distance z, and that means this has an unit. The unit of xi divided by the unit of distance. If it is in meters, so some unit of xi divided by unit of meter. Also, in this equation, you have the second order dispersion coefficient beta. So this beta 2 is also something which has some units. So also Pritam asked another question, sir, can you explain why the pulse is broadening time and spatial domain? So pulse broaden, okay, I'll come to this answer a little bit later. Let me explain about the normalization of nonlinear Schrodinger equation. So the normalization of the nonlinear Schrodinger equation, as I mentioned, we did it because we want to solve this numerically, and it will be useful to have a normalized form. And when you normalize, you will get two very important parameters out of that. This normalization automatically gives you two parameters. One is called the dispersion length, which is mod of beta 2 divided by T0 square, where T0 is the input pulse width. You normalize with certain parameters, and input pulse width is one of the parameters. Then you can also get another quantity called the nonlinear length. And this nonlinear length is defined by LNL. This nonlinear length, by definition, is 1 divided by gamma P0, where gamma is a nonlinear coefficient and P0 is a peak power. And if you check these two values, beta 2 divided by T0 square, which is the definition of dispersion length, that the dimension, if you check, you will find both the cases the dimension is the dimension of the distance. So this two distance is very, very important, because the value of beta 2 is known to you, value of T0 is known to you, value of the propagation nonlinear parameter gamma is known to you, and value of the peak power known to you. So these four values, suppose known to you. then you can readily calculate the dispersion length and nonlinear length. And this values basically gives you the idea that with this given value, whether the dispersion will be dominating or the nonlinearity will be dominating. If dispersion is dominating, you will find that LD, the value of the dispersion length, will be much less than the value of the nonlinear. That means the dispersion will appear with a very short distance. On the other hand, if the value of nonlinearity is less, the nonlinear length is less, that means the nonlinearity will appear to a very small distance. And this basically controlled by the parameter gamma and P0. So if you make a ratio LD divided by NL, this ratio will come into the picture if you normalize that properly, the equation. Then you will find that this value, if this value is 1, then we have nonlinear length and dispersion length same. That means two effects seems to be cancelling each other. And for that case, you will get the fundamental solution of that equation, and which is called the fundamental soliton. And the soliton solution is already there in the notes, and it was a homework that please check whether it is a real solution or not. If you put this solution, you will find this is really a solution. So this is roughly the answer of why we should make it normalized, because it is important to solve this numerically, also analytically. And numerically, it will be very much easier to solve a normalized equation rather dealing with something which has some unit. Next question I like to address, which is asked by Pritam also. And he asked that, can you please explain why the pulse is broadening in time and spectral domain? Well, the pulse is broadening. The very physical reason is, if you launch a pulse in a dispersive medium, it broadens under dispersion. That you need to know first. Either it is a diffraction or it is a dispersion. If it is a spatial domain, you can say this is a diffraction. If it is in temporal domain, it should be dispersion. So what was dispersion? We discussed in our course also. The dispersion means the refractive index should be a function of frequency. So when we launch a optical pulse, if you remember that optical pulse is generated as a superposition of many different frequencies. So I have a many different frequency, plane wave, and I add all together. When we add all together, they will form a bit, and that basically bit is nothing but our envelope. So the formation of the envelope, during the formation of the envelope, we add different frequency component and generate a structure which we call the envelope. Well, now if these pulses are allowed to propagate in a dispersive medium, what happened that different frequency component will going to travel at different speeds. Red component will travel at different speed, blue component travel at different speed, and there will be a gap between these two. It is exactly like 100-meter race. If you find the starting point, all the runner are in the initial line, and they are not dispersed during, because they are in same position. But as soon as the race starts, then what happened? That somebody is running a little bit faster compared to other, then there is a dispersion between this. So somebody is running faster and somebody is running not that fast. So there is a difference in space. Exactly that thing is happening here. So if some portion of the frequency is moving as faster and some portion of the frequency is moving slower, so there is a gap in between, and this gap one can observe in time domain in its counterpart, and in time domain you find there is a broadening. Detailed calculation, if you calculate, you will also find that this broadening is because of the dispersion coefficient. We have a dispersion coefficient, and this second order dispersion coefficient, which is generally known as group velocity dispersion. This group velocity dispersion is not same for all colors. For some colors it is different, and for the other colors it is different. So there is a gap. So there is a difference between the velocity, and as a result, what you get, there is a spreading of the light, and spreading is happening in time domain for temporal pulse, and in spatial domain it is happening in spatial domain, which is due to the diffraction. And that we also know diffraction means the light is not moving in a particular path, rather it is spreading. This path is spreading like a torchlight. If you switch on a torch, you will find that the light is spreading over the distance. Exactly the similar phenomena you can find in time domain. And in time domain, it is happening because of the dispersion, and in frequency domain, in spatial domain, it is happening due to the diffraction. So this is roughly the reason. If you are okay with this explanation, you can say that it is fine. Otherwise, if you have any doubts, you can just write the comment in the comment box in live YouTube channel, and I'll be happy to address that. Well, this optical soliton and all these things are a little bit advanced concept, but in this course, I wanted to cover all this because this is quite relevant. And once you understand the different aspects of nonlinear optics, then once you understand how the pulse is propagating in a linear medium, and during the study of the dispersion, we did it in a very detailed manner, then the same technique you can use here also, and you can calculate from the scratch. You can calculate the dynamics expression of the light propagation in a nonlinear medium, and eventually which gives you something called cell-phase modulation, and a combination of cell-phase modulation and dispersion gives you something called optical soliton. The integrable form of the optical soliton is also done. So directly I try to solve with this differential equation. This calculation is entirely given. The detailed calculation is given in one of the important book, and that book is called the Introduction to Fiber Optics by Ghatuk, Professor Ajay Ghatuk and Professor Tyagarajan. Very good book. And from that book, you will find that in chapter 16, I believe, all these calculations are there. Apart from that, if you want to study more about nonlinear waveguides, nonlinear fiber optics, there are few excellent books. One of the major books that is used all over the world, that is called the Introduction to Nonlinear Fiber Optics, or sorry, Nonlinear Fiber Optics by Professor G.P. Agarwal. This is like a Bible to us, and in that book, all the detailed aspects of nonlinear fiber optics are there. In that particular book, you will understand the concept of optical solitons, the concept of dispersion, the concept of nonlinearity, and many other things associated with this. So with this note, I'd like to ask again, if you have any questions and queries, please ask me. So if you have any question, then I'll happy to respond to your question, address your question. And if you don't have any question, then I'd like to end this session, because I have already covered whatever we have done in the course today, the live session 3. I just need to discuss about the nonlinear optics part, nonlinear waveguide part, which I already discussed in this 40 minutes. So now I want the question from your side. If you have any question, those who are live, they can ask me the question. If you have any doubts, if you have any queries regarding this particular topic, otherwise I need to switch off the session. Do you have any question? Please ask. If you have any question, please ask. I'm waiting for your questions. Okay, I got another question, and this question is interesting question, and the question is, he asks, what is the unit of psi? The unit of psi should be root over of what? It should be root over of what? Because if you make a mod of psi square, then it should be the unit of power, that is watt. But if you not make a mod of square, then it should be root over of watt. So that's all. It should be root over of watt. Any question? Any other doubts? I'll be happy to respond. Okay, so another question I got from Pritam. Again, a very interesting question, and he mentioned that what happened if LD is not equal to NL. So if LD is not equal to NL, then if you launch an optical soliton, it should not be a fundamental soliton. It should be something called higher order soliton. And in order to find out the higher order soliton, for example, the ratio of LD and LN is not 1, rather 2. If it is 2, you will get something called higher order soliton. And this higher order soliton will evolve in a different way. It will be evolving in a different way. There will be certain periodicity and complicated kind of structure one can see for higher order soliton. So it will not be the way the soliton is moving, like one Gaussian kind of pulse it is moving. Rather, it will move like a Gaussian, and then it changes shape, and then again after a certain period it comes back to its original shape, and something like that. So I can share my screen. Since you asked this question, I am interested to show you. I don't know whether you can see this. I can share my screen. And in this screen, if you look carefully what is going on, Then this is the figure, and this n value is basically the ratio of LD and n. On the left hand side, you can see the periodic evolution of the solitons. So these are the solitons you launch, and these are the higher order solitons because LD and Ln are not equal, and as a result you find that there is a periodic evolution and very complicated kind of structure you can get. And if you launch the right hand side, the figure, whatever you can see, this is along the distance it is propagating. The right hand side, the picture you are seeing, is called the mesh plot. In a mesh plot, you can capture the intensity, how the intensity is varying, and this color basically tells you the intensity. That means if you have a bright blue color, then you have a higher intensity. So these higher intensities are here, represented by this blue color. And you can see that there is some sort of splitting of the pulse, and then again it merges, and then again splitting of the pulse and merges, something like that for n equal to 3, n equal to 4, n equal to 5. These things are much complicated. So in a word, I must say that there will be a very complicated kind of dynamics one can expect if LD is not equal to NL, and it is called the higher order soliton. It may be fractional also. It is not necessary that LD divided by NL, this ratio has to be a whole number, like it's shown here, 3, 4, 5. It can be 1.5, 1.2, 1.8, etc. In all the cases, you will find there is some sort of periodic evolution. I hope this figure helps you to understand. Yeah, as I mentioned that this figure helps you to understand how the higher order soliton will evolve, and that happens when LD and Ln are not equal. This is a little bit advanced stage compared to the course. In this course, our concentration is much on the waveguide, not on the nonlinear phenomena that is happening inside the waveguide. There are a huge research going on that particular field, the light matter interaction and the ultra short pulse dynamics, which is happening inside a different kind of waveguides. And optical soliton is a part of that. This is a starting point. And if you start understanding the optical pulse, the behavior of the optical pulse in nonlinear domain in the form of optical soliton, then gradually you can build up. But these are entirely a very advanced level study compared to the course we are having right now in our hand. But it is relevant, so that's why I thought I should at least give you the basic idea of exactly what is going on. And that was the goal, to include everything in this nonlinear part. Any question, any understanding? So I like to discuss. We don't have much time. I guess we have only 5 minutes time in our hand. So within 5 minutes, I think I should stop. So another question I have, sir, can you please explain why the derivative is 0 in boundary condition? So I believe we were asking the derivative 0 in the boundary condition for the optical pulse. And if you look at the optical shape of the optical pulse, it is a bell-shaped thing. And bell-shaped means it is having a maxima at some point, and gradually both the side it is decaying. And when at the boundary, if you go to it almost parallel to the level or almost to zero. So if you make a derivative of that kind of thing, so essentially we'll get zero. So that's why for bell-shaped structure, suppose you have a Gaussian pulse, and if you calculate the derivative of the Gaussian pulse in the boundaries, you will essentially get, even if you do numerically, you will find it is zero. So that's why we took this boundary condition as zero here, because of the structure of the pulse. It is not having any kind of hinge or anything at the boundary. It is very flat. We have another 2 to 3 minutes. If you have any question, Pritam mainly was the student who asked this question, but if you anyone is there, so they can ask the question quickly, because the time is not there in our hand. The next speaker, the next live session will be there, so I believe we need to stop quickly. One question again we had from Pritam, and his question is, I think this should be the last question in this session. So let me quickly address this question. The question is, sir, can you please explain how evanescent wave propagates? Well, the propagation of the evanescent wave we discussed in our class in detail, and if you remember that evanescent wave is something which is generated very in the vicinity of the core clad boundary. And if you go too far away from the cladding region, then the amplitude is uh, decaying very rapidly, exponentially. But in the cladding region, still we have a contrast of refractive index as far as the optical fiber is concerned, because optical fiber has a core region, then there is a clad, and then we have a air. So clad can be act as a some sort of high refractive index medium, and some sort of energy can pass through this layer also. So this is the way this kind of cladding modes mainly are propagated. Evanescent wave are also are some sort of wave that is very associated, very adjacent to the core cladding boundary, and they can propagate with the pulse itself, because the mode itself, because mode is propagating inside the fiber in a similar way. It basically drag down the evanescent waves, and evanescent wave also are propagating in the cladding region, because the core clad boundary it also experiences in optical fiber. Well, I believe we are running out of time. It is already 6:50, and the maximum session has to be 50 minutes. So I think we should stop. So let me stop this session right now, because the next speaker. Should I stop? Hello.
Yes, sir, you can.
Okay. So thank you. So I think the session is over right now. So let me